This is AP Calculus Unit 11, Lesson 5, and that means we are done after today. This is our last lesson of new stuff.
Scared. Like, this is kind of like sad. Like, can we like just take a moment to say
It is kind of sad. I mean, there's plenty more that I can teach you about calculus. This is everything that you need to know in order to get a 5 on the AP Calculus exam, so we're going to review everything. But as I kind of mentioned before, there are some things that I don't explicitly teach, like I teach you how to do 3/4 of a problem. I can teach you that last 1/4 if we want.
Oh, I remember.
So let's talk about the difference between basic and advanced volumes of revolution. So I'm still revolving around the x-axis in this first example. And if you're familiar with calculus terms, that means we are going to be doing the washer method. There are really, really advanced volumes of revolution. They're just different, I guess. And some of those are called shells, if you want to look them up. But for now, I'm just going to go into a different type of washer. So I'm going to revolve this around the x-axis. What does that look like? That means that this point here comes down there, and that's the hole that it makes. That means our red is now on our inside, and it comes out like that. I'm trying. And our blue comes out like that.
Oh my god.
And looks like that. So I guess if I add these lines like this, it makes it look better, maybe.
Oh.
So I'm revolving around the x-axis.
Oh god, Mr. Sindel.
I know, it's difficult. It comes with practice. I definitely need more practice, as you can see here.
Wait, I'm kind of confused about like what it is. Like,
What it is?
like the shape.
The shape? Okay, I made a program yesterday. I can pull that up here really quick. But it's not exactly this function.
It is confusing.
It is, and it's hard to visualize too. So, GeoGebra, if you want to open up, there's probably a better way to program this thing. I didn't have as much time as I would have liked. Open recent. This was our 11-4 visual.
Yeah.
If it wants to open. Oh my gosh. Quit unexpectedly. Let's make this smaller. What's going on here? Please work. Yes, that's one I want to open.
I have a goldfish. Yeah. I thought you gave up goldfish. Nope.
Alright, so I'm doing this shape instead of the shape that we were working on, which is a little bit different. So what does this thing look like when it rotates around the x-axis? So I got a 3D view up here. And what I can do is I can rotate this thing all the way around the x-axis. So what I can actually do is I can right-click this one and it will... Oops. I want to animate it. So what you can see over here is if I have this basic shape that started on the XY plane and I come out into the third dimension, this area is sweeping around the x-axis, and as it sweeps, it's creating a volume for the shape.
That makes sense. Oh.
And it will
So,
eventually
like,
be, yeah.
How is this like, we know it's different than the other ones because like in the other ones it was like 2D kind of, like it didn't sweep around.
It was still sweeping around for volume. As soon as you hit volume, it's popping out of the XY plane into the Z axis. And I think in the video I showed you girls a picture of what that 3D object looks like.
Yeah.
So
as
this
soon
is-
as they talk about volume, you're gonna think this.
You're going to think either swinging around some x-axis or some axis, and you're also going to be thinking about what happens if it just pops out as a square, pops out as a triangle. Triangles and semicircles, I talked to John yesterday, and he said that they're really rare. They come up on BC calculus all the time, but in AB, they basically never come up, so that's why it's not taught in our lessons. Square does come up, though. So the square is really the only one that you need to know.
What happens if like a triangle does come up though? Like
If a triangle does come up, that's something that you can talk to me before or after class. For example, Joy came in a little bit early yesterday, and I taught her triangles.
Oh.
Perfect. So that's our visual of what's happening. It's sweeping around the x-axis and creating this cool volume. All right, so we have this volume. So I'm going to make this... That was our basic problem, our basic volume. Let's do the advanced volume. The advanced volume just means instead of rotating around the x-axis, I'm going to rotate around something else. Let's instead rotate around I don't know, let's say y equals -1.
Oh god.
So we can say this is now y equals -1. I'm rotating around this, which makes it a bigger shape. So obviously if it's a bigger shape because it's just more area, I guess, that it's sweeping around, then the volume should also be bigger. Let's see if Mr. Sindel can attempt to draw that. So this is going to come down, all the way down here. And this blue is going to come, sorry, it's going to be red on the inside, so I'll do red on the inside. And then blue on the outside. And there's our black. Oh, that's white. I want to use black. Oh gosh. Not too shabby. I'm getting better.
Not me.
Alright, so now this is a bigger volume. You can think of it kind of like a bigger pot. A bigger pot, even though the walls might be the same width, the walls that are exactly the same width here, because it's a bigger pot, you need more material, more volume in order to make that pot. That's the way that I visualize this. So this will have more volume. And you can change this axis of rotation wherever you want. And for all of today's homework, it's just going to be a horizontal axis. If you start doing a vertical axis and you start rotating it, you need a new way of calculating volume, and that's where you get into shell method instead of doing washer method. All right, so everything here, it's still a washer. Are we done drawing these? Can I go on to the next slide?
Yeah.
Perfect. So what do those cross sections look like? So the cross section, again, if I cut this right here, what does that cross section look like versus this one getting cut? So our next slide is talking about cross sections. Cross sections. So our first cross section, what was the outside? Outside was blue, so I'll make a blue circle. And then the second one was a bigger blue circle.
We're gonna lose it.
First one was inner red. The second one was a bigger inner red. I'll center those in a sec. It could be centered a little bit better, but oh well. So both of them have about the same width for the walls, but you'll notice that the walls stretch farther for that cross section. And always try to visualize this between what we just found on the last slide. So if I cut it in half, that's what the cross section looks like. Cross section over here is bigger. So we need to come up with a formula today before we go on to the homework. How do we calculate it when we start rotating around different axes? Once we get that formula, we're done with the notes. I can probably end the notes right at the end of this slide, hopefully. So I need to find the formula. So now we're working on the formula. And to make sure that I have enough room, I'm going to shift all these up to the very top. Good enough. All right, I can make those come down a little bit. All right, so the formula for this one, this is a review. What did we have yesterday?
Top squared minus bottom squared, or pi times top.
So yeah, I like top squared minus bottom squared because that helps us out. But eventually I do need the actual formula. Top squared minus bottom squared. Then what do I do with that?
Put brackets around.
Yeah, usually we put brackets around it, and then we have to get.
Or wait, no.
So
dx.
dx, yeah. If everything out here was squared, that would make it a square section, and those wouldn't be squared. And then we're missing the thing that says count up all of these.
So
Integral between A and B, perfect. And we're missing one last thing. Pi, because that's where the area of a circle gives us pi.
Wait, but what I don't
Pi
get
r
is,
squared, pi
why
r
are we
squared.
taking the integral?
Integral is the thing that says sum them all up. Sum up an infinite many number of
Oh.
circles.
Okay.
Yeah, I'm trying to think, was Euler the one that, no, it was Leibniz, I think, that popularized the S, the sigma notation. Fun fact. Okay, so what was the actual formula for this guy when we actually have...
So it's the same thing, but inside the brackets is f of x.
So same thing, so pi from A to B, and then which one was f of x? And you have to, the top one in this case was f of x. So it's going to be f of x, all of that squared,
Minus
g of x,
squared.
all of that squared,
And
put brackets around it, dx. Okay, perfect. These represented the heights. For example, just making sure we understand this from yesterday as well, a little bit of review in here. That was a height, and this right here is a height. This was the height of f of x, and the height was easy. You just go 0 and then you go to f of x, so 0 plus f of x. And the height for, I forgot the parentheses here, and the height for the red radius was just g of x. We didn't have to add anything special because you literally go from 0 to g of x. But now it's different. Instead of going from 0 to g of x, the radius here comes from all the way from y equals -1 all the way to g of x. So we have to have some way of saying, hey, your radius needs to be a little bit longer. How do we get that radius, that new radius here versus the old radius? The old radius was just here. Well, it should be a straight line, I guess. Find the distance from -1. Yeah, exactly. So how do I say that mathematically? Find the distance from -1 to f of x. Your height, yeah, height of f of x, but then how do I include that -1 also?
Subtract 1.
Yeah, so you just subtract it. So our general formula can turn into this. And should we write this in red? We'll do our setup here, so this isn't going to be our final formula. So we need our pi still, integral between a and b. And so our top was f of x, so we were going to say f of x. And then we need to say subtract the -1, or adding the 1, which makes sense, right? So if we're subtracting whatever coordinate we have here, we're really adding 1, and that makes sense because our radius should be bigger. This is negatives, makes it plus, so, and then all that is going to be squared. That was our radius, and we're going to square it, and then we're going to do minus our g of x, and g of x also needs to be bigger. How are we going to do that?
Same thing.
Same thing, yeah. So minus 1, minus 1, and then that is our radius, so we're going to square that radius, and then all of that needs to be multiplied by our thickness, which is dx, and we have our formula. So now we just need to do our general formula, and we're done. And here it is. I'll do it. I'll put a star here to let you know this is important. It's going to be pi integral between a and b, and so we have to be careful about top and bottom, because sometimes I might be rotating around a line up here, in which case it's not going to be top minus bottom, it's going to be the outside minus the inside. So I'm going to change my terminology a little bit here, and just to make sure, let's back up, really understand. If I'm rotating around this line right now, my top is now g of x, because g of x is going to be on the outside when revolving around this line.
Oh, so it's like outside minus inside.
It's going to be outside minus inside now. Okay, so this is going to be, instead of saying just f of x and g of x, I'm going to say outside minus, and then I'm going to say axis here. This is going to be the axis that you're revolving around. All of that squared minus inside minus axis. And this is in the way, move up, squared. All of that needs to be multiplied by our thickness to get volume, dx. And we have our general formula. And remember, axis is just a number. It might be a negative, so you might have a double negative. You might just have a number. Cool. That's all we have for the notes. So go ahead and write your summaries, and we'll resume the video when we talk about an example problem. The front page is pretty easy. The front page of the homework is just doing the setup. The back page is actually calculating what that is on our calculators. All right, so this is number 3 on the homework. Number 3. And again, this one is pretty nice because we don't have to evaluate. Do not evaluate. All right, so we need to set this up. So we have our, we'll just say volume is going to be equal to, make sure your pi is on the outside. You'll have the integral between a and b. We know our a is going to be 0. We don't, oh, we do know what our b is. Our b is going to be 1/2. 1/2. And I'm going to start my bracket here, my parenthesis here. All right, I need to know what is my outside function? I know.
I'm in the outside function.
So to know where this is, I need to have my line y equals 1. Y equals 1 looks like that. So I'm rotating around this line, which means my outside function will be this line right here. I know that this other line is sine because sine comes up and then curves down like this.
Yes, I know.
So So that means that this one must be the other one. This one must be 8x cubed. And that makes sense because 8x cubed, anything with x cubed looks like this. So this is going to be 8x cubed. And I'm going to subtract my axis. So it's 8x cubed minus 1. All of that quantity squared minus, and this is going to be sine of pi x minus 1 quantity squared in your square bracket dx.
So to figure out the outside, you kind of just imagine it like flipping over itself, sort of, and then like which line would stay on the outside.
Yeah, the one that stays on the
Okay.
outside, exactly.
And then you know that, okay, and then you just identify like what kind of line it is to know which function.
Yeah.
Okay.
Are there any other questions on this one?
No.
No. All right, so let's move on to number 4. Number 4 is pretty difficult. All right, so number 4, we spent quite a bit of time working on this. Let's see what we got. So the volume, that's going to be equal to pi times the integral, and from here about to here. And we don't know what those points are, but I think everyone in here found them more or less, I would hope. So let's go ahead and do that really quick with Mr. Sindel. So I think the fastest way to do this is to just graph both of these. So I have natural log of x and x minus 2. So I'll say natural log of x and x minus 2. Window, it's definitely between 0 and, I don't know, let's just say 5. That's a good value to choose. And if it's outside of that, then we can just make our window bigger. So there's our natural log of x. Remember what natural log of the x always looks like? And okay, it looks like it's intersecting around there, So second trace, there we go. And we're going to calculate an intersection point, so 5. And I'm going to try to find this one. So first curve, enter. And our guess, I'm going to guess around 0.2. And I got 0.15 round to 9, so 0.159. 0.159, and that second one, so I do the same thing, second trace, intersect, enter, my guess is around 3. Around there. 3.14619. So it's not exactly pi, but it's pretty close to pi, actually. I thought it was pi at first glance, but so it's 3.146. All right, that means our integral, coming back here, is going to be integral between 0.159 and 3.146. And let's set up our bracket, our parenthesis. So we're rotating around y equals -3. So y equals -3, that's somewhere down here. So that means our outside function is that curvy one, that's the natural log function. That one's natural, maybe we can label it like this natural log. And that one is just our x minus 2 function. So natural log is going to be on the outside. So we say natural log of x, and we're going to subtract -3. So subtract -3, and that's going to be squared. And we're going to subtract, and we have x minus 2, subtract -3, that quantity squared, and dx. Perfect. And obviously you can see, okay, that's going to be turned into a plus. That's going to turn into a plus as well. And then we plug it into our calculator and solve. So let's do that. So let's get out of this, and we're going to do second power of to get pi times math 9 integral, and it's going to be integral of, so this is our y1 function, I believe. Let's just double check that. Yeah, y1 was natural log of x, so it's going to be far as right, enter. I guess that's too much work. You could just enter natural log, I guess. Natural log plus 3. Oh, I forgot my parenthesis. So if you need to enter it again, it's second insert parenthesis. So end the parenthesis around there. We're going to square that. And we're going to subtract. I can just simplify this really quick and just type it in my calculator here instead of doing y2. I could just say this is going to be x plus 1. X plus 1 quantity squared. So that's my entire function. Good. Let's do comma. That's going to be with respect to x from 0.159 to 3.146.
Aren't you forgetting the plus 3 on the second?
So, not exactly, because I have x minus 2 plus 3. Minus 2 plus 3 is just plus 1.
But if
That's
I
fine.
just put it in like, if I enter my y2 and then I have a plus 3, it should get this.
It should give the same thing, yeah. So this is approximated by 34.199. 34.199. And There's our answer. And let's not have units. Don't put units Q because that's just too much work and you're not going to get any extra points. So 34.199. Perfect. Questions on number 4?
No, it's just that I think I did my parentheses wrong because I like entered that, but then I got a different answer.
Okay, yeah, practice with the calculator. I can come by if you need more help.
Would they dock you if you're like 1 digit off?
You did 198 here?
Yeah.
Yes, they can dock you for being 1 digit off. Because in the answer key, they'll say 34.199 or 34.198. If that was the case, then you wouldn't be docked, but that is not in the answer key.
Yeah.
They need that to be a 9. Actually, that one would be an answer key because that would be truncated. So 198, for this problem, no, you don't need to truncate. But just be careful because some people enter in pi there, and it wasn't exactly pi. That was my mistake also when I first did this problem.